Welcome to Data Science with EJD. In this video, I'm talking about clustering evaluation metrics. We've come across them, along the line when we're talking about the clustering algorithms in unsupervised learning. So let's just zoom into them to understand them better. Uh, so introduction to clustering evaluation. Clustering groups data points based on similarity without predefined labels. Yeah, I mean, we've talked about clustering algorithms, right? And we know that they group data points based on similarity without predefined labels. Since we are working on unlabeled data, right? So you're just looking for patterns and similarities and things like that. So evaluating clustering quality is essential to validate if the clusters formed are meaningful, coherent, and useful. So the question is, why evaluate clusters? Of course, we know we need to assess quality of clusters, the compactness of the clusters and their separation. We want to compare clustering algorithms or hyperparameters. We want to validate results against known labels if available. And want to guide model tuning and selection. That's why we need to evaluate clusters. We want to know if the clustering you've done is worth it. So categories of clustering evaluation metrics. We have two broad categories of clustering evaluation metrics. They are internal metrics or external metrics, otherwise known as intrinsic evaluation or extrinsic evaluation. For internal metrics, use only features and cluster assignments and no need for, I mean, internal metrics use only features and cluster assignments, and there's no need for ground truth labels. They measure how well clusters are formed based on cohesion and separation, and they are useful when true labels are unknown. This is common in unsupervised learning. And for external metrics, which is also extrinsic evaluation, they require ground truth labels and they measure agreement or similarity between clustering results and known class labels. They evaluate how well clustering captures actual classes, and they're useful for benchmarking and supervised comparison. So the next thing is to look at some key metrics and their theoretical foundations. Of course, mostly these things are rooted in mathematics, talk about statistics, probability, calculus, and so on. So we have the silhouette score. You remember we came across silhouette score when we're talking about, I think K means clustering. So silhouette score and the elbow method helped us to determine the number of clusters, the optimal number of clusters we should have. So silhouette score is an internal metric, and the concept is that it measures how well each data point fits within its own cluster compared to other clusters. So it's more like you're trying to really evaluate why a data point should belong to a cluster and not the other one. So definitions for point I. So if you have a cluster point I, a data point I, right? So A of I is actually the mean intra-cluster distance. That's average distance to points in the same cluster. Then B of I is mean nearest cluster distance. That's lowest average distance to points in any other cluster. So using this now, the formula becomes the silhouette score of the data point I is actually B of I minus A of I. That's the mean nearest cluster distance minus the mean intra-cluster distance, all about the maximum of these two things. So that gives us uh, the silhouette score. An interpretation is such that S of I is approximately if S of I is approximately plus one, it means you have your clustering is good. So you have the data points well clustered. If S of I is almost zero, that means that you have on the decision you are on the decision boundary between clusters. Then if S of I is less than zero, that is possible misclassification. Overall silhouette score, so is the mean of SI over all points. So you take the silhouette score for each point and you average them out, I mean that sounds like a lot of task already, depending on the kind of data points you're dealing with. So advantages, it has an intuitive interpretation. I mean, the explanation just tells us that it's a distance that we are simply talking about. You take each data point and just measure its distance from every other data point within its cluster, and then you measure that the distance of that data point from every external cluster again. So that's really easy to understand. Then it works well for convex clusters. Convex clusters will be clusters that are well packed, right? Like all together or something like that. So the limitation is that it is expensive to compute for large data sets because you are looking for pairwise distances for both intra-cluster, for within the cluster and outside the cluster. So it can struggle with non-convex shapes, right? So that's the silhouette score right there. So let's talk about the um Davies-Bouldin Index, which is an internal metric. The silhouette score is actually like we saw is an internal metric too. But although it sounds to me like both internal and external because you're also doing okay, well maybe that's on the basis. So let's talk about the Davies-Bouldin Index, which is an internal metric. So this quantifies cluster similarity based on ratio of within cluster scatter to between cluster separation. Okay. Definitions, you have S of I, which is the scatter. That's average distance of cluster i's points to its centroid. So there's a center point for each cluster. So the average distance of the of cluster i's data points to its centroid. Then you have MIJ, which is the distance between centroids of cluster I and J, right? So the formula is you have R sub ij equals Si plus Sj all over Mij, where Ri is the maximum of Rij, where J is not equal to I, you know. And then you have dBi, which is equal to 1 over k. That's the Davis-Bouldin index, right? So that is 1 over k. You need Rij to compute it. That's why we're doing this. So dBi is 1 over k, summation from I to k of Ri. Of course, Ri being the maximum of all the Rijs we've computed before. Then the interpretation is that lower dBi indicates better clustering. So it is compact and well separated clusters. Then the advantages is that it is fast to compute, it's sensitive to cluster compactness and separation. The limitations, it assumes spherical clusters with similar sizes, and it can be biased by noisy data. So it can, noisy data can make it can misclassify easily. Basically, that's all that is about. And another metric is the adjusted RAND index. So far we've talked about the silhouette score, we've talked about the Davis-Bouldin index, which are both internal metrics. Now we're talking about an external metric, which is the adjusted RAND index, ARI. So it measures similarity between two clusterings, predicted and true labels, adjusted for chance grouping. So counting pairs of points assigned in the same or different clusters in both assignments. So the adjusted RAND index, ARI, is actually Ri minus the expected Ri all over the maximum Ri minus the expected Ri. So where Ri is the RAND index and expected Ri is the expected value by chance. So the interpretation is this: when you have an ARI of 1, that's perfect. You have perfect agreement in the clustering. If it is 0, that's random labeling. If it is negative, that's worse than random. The advantages of ARI include the fact that it's correct for chance and it's applicable to varying cluster sizes. The limitations include the fact that it requires true labels and does not measure cluster compactness or shape. So in summary, uh, summary comparison table now. So what we are comparing the silhouette score, the Davis-Bouldin index, and the adjusted RAND index. First of all, silhouette score is internal, while Davis-Bouldin is internal also, and adjusted RAND index is external. Silhouette score requires label. Davis-Bouldin index does also require. I mean, silhouette score does not require label. Davis-Bouldin index does not require label. Adjusted RAND index does require labels. And then silhouette score falls within -1 and 1. All right. So 1 is the best performance, while -1 is the worst performance. Then the wouldn't lie between 0 to infinity. So lower is better. Lower means better clustering. For silhouette score, higher is better clustering. The optimal goal there is to maximize. And for Davis-Bouldin, for silhouette score, right, the goal is to maximize the score to get, you want to be as close as possible to 1. And for Davis-Bouldin index, the closer to 0 you are, the better. So you want to minimize the Davis-Bouldin index because lower means better clustering. For the adjusted RAND index, it lies between -1 and 1, just like silhouette score. So higher it means better agreements with labels, and you want to maximize that as much as possible. Now let's look at a practical Python implementation example. Of course, using the popular iris dataset as usual. So let me bring up the line numbers. Okay. So want to see all these metrics on this now. So again, lines 1 to 5, they are there for because anytime we're using k-means clustering, that is also always necessary to avoid MKL memory leak on Windows, right? So of course the libraries we need scikit-learn, we need to import data sets from there. Then from sklearn cluster, we need k-means, we need preprocessing standard scalar, We need SQL metrics like silhouette score, Davies-Bouldin score, and adjusted rand score. Those are the three metrics we've been talking about. So here you can load Iris data sets. We've done that quite a number of times. So of course, though we are talking about unsupervised learning, right? But we also need true labels. For external metrics, you need labels. So now we see why sometimes, though in unsupervised learning, you still have some targets like that because they are useful for external metrics. Then you can standardize to normalize the data, the variables that you're interested in. So this is important for distance-based metrics in particular. Then you want to apply k-means clustering with three clusters. So of course, here you can use the elbow point, the elbow method, and all that to find where how many the optimal clustering number. But here we're taking three randomly. You can change it if you like. Then here we're training the k-means model on the data set we have. So k-means n clusters is k is 3, right? Random stage is 42 for reproducibility. Then you can now predict based on that. So y-pred is k-means fit predict x kills. Then you can now calculate the metrics. So you have the internal metrics like the silhouette score. So you have silhouette underscore score into x killed y-pred, and db index, that's Davies-Bouldin score, into x killed y-pred. Then the external metric is ARI score, that's adjusted rand score rather, into y true y-pred. And then you can display the results now. So we run this. So it takes oh yeah, it's done. Yeah, so we have the results. So the silhouette score is 0.4. Okay, to one decimal place. Silhouette score is 0.5. Davies-Bouldin score is 0.8. Adjusted rand score is 0.4. I mean, generally, you discover that the model, the k-means clustering doesn't do really well with this in this situation because, of course, the silhouette score is the only average. The adjusted rand score too is also average. Now, the Davies-Bouldin index is particularly bad because this is okay, well, I mean, it's between 0 and infinity, so maybe we can still take this as a good score, right? 0 and infinity. So the Index should be as close to 0 as possible. So maybe we can work with this. So on the whole, on the generally, right, the metrics show us that the model performs on the average on this. So we can do some tuning here and there if we want better results, right? So, explanation of code is of course, the standard scalar scales features to zero mean unit variance, which improves clustering performance. So you're normalizing the features. Then the K-means performs clustering just like silhouette score and Davies-Bouldin score evaluates cluster quality internally, while the adjusted random score compares clustering against true class labels. Interpretation of results now. Of course, this is just an example. I mean, for in that place now we got roughly 0.5 for the internal scores. So if you have a silhouette score, this is an example, not what I'm not referring to exactly what is up there, right? So if you have a silhouette score of like 0.55, so it's moderate to good cluster cohesion and separation. So we can say for the values we have here now, the 0.47 for silhouette score and the 0.43 for the adjusted rand index, right? So we can say that it's average, it's average, moderate to good cluster cohesion and separation. So if you have a Davies-Bouldin score of 0.66, it's low value. That's a low value and it indicates compact and well separated cluster. So it's good. Then adjusted rand index 0.73 means high agreement with true labels, good clustering accuracy. So for what we have here 0.43, it means we have just like average performance like that. Okay, so you can have additional notes and best practices as follows. No single metric fits all scenarios, so you need to use multiple metrics for comprehensive evaluation. Internal metrics are essential when ground truth labels are unavailable. External metrics are crucial for benchmarking and validating clustering models when labels exist. So if you have labels, like if you're working with a data where you can have, I mean, most data we've been using for machine learning, you can easily separate them into features and targets. So in that case, you can easily do the ARI. Then you can consider data set characteristics like size, noise, cluster shape when choosing metrics. Then visualize clusters, e.g. with PCA or TCNA to complement numeric evaluation. We've done this in previous videos, so you want to refer to those ones, especially where we talked about clustering in general. Okay. So with this, I come to the end of this video. Let me know how helpful this has been for you. And if there's something you'd like me to try out, feel free to let me know. Um, you can, you can, of course, already subscribe to the channel if you haven't done that already, and hit the notification bell so you can always get alerted each time a new video is released, right? Um, um, on my channel, you can become a member at 3 levels. So click on join and you see the possibilities and feel free to join. There are different levels of benefits you can get by joining. Be sure to share this video so that more people can have access to it. And then, of course, my code sheets are available on Google Drive. Just look at the description on YouTube or Facebook, and then it's take you there. Download all the code sheets and follow along as I do this thing so you can learn hands on. Till like, okay, yeah, bye.